So, remember that when we talk about these things, everything's a give and a take, right? There's a trade-off for everything. If you increase the specifications or the specificity or one of these factors, you okay? Okay. If you increase one of these factors, it's going to take away from somewhere else. So if you do more tests, it takes away time and the ability to turn tests around, right? So for example, if you sample more, you'll have to have more samples, you'll have to have, it becomes counterproductive at some point, okay? So keep that in mind. When we talk about these specifications are going to be the requirements that you would hand down to the people that would actually do the work. And then fulfilling those requirements should give you the right mixture of these previously talked about points, okay? They're going to fulfill the objectives that you're looking to fulfill. For example, if you need to test 1 billion people or 100 million people, you can't have a test that takes a long time, right? We saw that with COVID. Remember when the first test took hours? How the hell are you going to handle when you have 100 million people that are sick? You can't test that, right? And that's why we don't even know, like the majority of COVID tests, even to this day, we don't know if they actually had COVID or not, because we couldn't test it. The testing took too long. So these are some of the different specifications. These could be included, though they are not the only specifications, period. Oh, is it not? You turned it off on me, huh? Okay. So these specifications could include sampling requirements, accuracy and precision, rate of false results, the selectivity, the sensitivity, the accepted blank values, recovery of fortification, or another way of saying that is spike recovery, calibration checks, and quality control samples. These are some of the ways you can ensure that your labs are performing within your specifications, okay? And so you'd give them quality control samples every week, and they have to come within this range when they do those, right? What does that do for you? Well, it tells you, are they getting the correct results from this, right? At least once a week. They're doing it correctly. So here's sampling requirements. You must collect representative samples, and analyte must be preserved after sample is collected. Otherwise, even the most accurate analysis is meaningless. The quality assurance always begins at sampling. If you give bad samples, then everything else you do from then on is garbage, right? Remember garbage in, garbage out? So literally, when you talk about these specifications, from the time you get the sample from the person, in fact, what sample you take from, wherever you're taking it, from then on, every single step you screw up is a step that could give you garbage. Because you could turn something okay into something that's garbage, right? Yeah. So, an example of where they did this wrong, lead levels in blood. I saw a group that was sampling and they had like a little card thing that you prick the person's finger, they put the sample on the card, and then they were shipping them off somewhere, and their shipping handler was leaving them for weeks and then shipping them on. So by the time they got it, the lead was separated from the blood and they weren't getting it back off. They had no way of recovering from that. And so every single test they did was negative, right? And of course, because they didn't know what the fuck they were doing, they didn't have another one of these where they'd put, blanks in, samples that they know what the result of. And so they didn't know that for half a year. They just thought they all, all of them were negative, which first off, in and of itself was kind of a stupid thing, right? You wouldn't expect every sample you get to be negative, would you? I mean, come on. Accuracy and precision. Again, this is within practical restraints. You need to consider the cost, the time, limited amounts of materials, manpower. It's not as simple as more is better, right? It's definitely not more is better. Otherwise, I would have had you do a 10,000 scan on the spectrometer, right? And you would have taken half a year to do it. It would have done you no good in organic chemistry. So what level of accuracy and precision will satisfy the use objectives? For example, if you're just testing if somebody has a minor disease that they're probably not going to die from, if you screw up, and they probably won't spread it to a lot of people and cause them to die, a 95% chance might be good enough, right? If you're testing somebody for something like AIDS, where, well, they do now have a cure supposedly, but it's not, it hasn't made its way through trials yet. But, it was uncurable for what, 40 years? 1 in 10,000 chance is probably really bad, right? Because then they go on and spread it to a bunch of people. Yeah, that was be bad. So what rate of false results is acceptable? False positive is going to imply that the concentration exceeds the legal limit when in fact the concentration is below the legal limit. That was what was happening where they had in COVID tests. You remember when they were detecting people had COVID when they weren't, and it came back as just thousands and thousands of tests that were positive, and they weren't. Again, that was because they didn't know the limit of the viral load that caused COVID to occur, and so they were giving false positives in a tremendous number of them, right? A false negative implies that the concentration is below the limit when it is actually above the limit. That false positive one, by the way, for COVID, that was entirely due to the CDC. They gave a legal limit for a COVID viral load that was way below what it should have been. Because they just, partially because they didn't have the data for some of it, but partially because they just were incredibly incompetent during the entire thing. It was just a fucking disaster. Anyways, selectivity and specificity. So distinguish the analyte from other species in the sample and thus avoiding interference. You will notice if you read forward in your labs, we actually do a lab where this is a problem. Where we detect, with one of the tests, we detect both magnesium and calcium concentrations together as one thing. And then we have to do a second test to tell us which is, I believe it's magnesium we test for. And that will tell us how much of that is magnesium, right? And so this is actually an issue in a lot of tests. It's actually very difficult to get something that's selective for just what you want. That almost never happens. Hell, your eyes, your ears, everything you use to sense in the first place has a poor selectivity, right? If you think about it, if you just go through your head and go through different scenarios. Selectivity, specificity. You want to try saying that with me? Specificity. Do it as 2 words, okay? It's hard to do it as 1 word. Sensitivity. This is the capability of responding reliably and measurably to changes in analyte concentration. Your detection limit of an analyte method must be lower than the concentration to be measured. If your detection limit is higher than the concentration to be measured, you will never know how much is in there. Well, you'll know that it's below your detection limit. By the way, you guys ever heard of homeopathic medicine? Funny thing about homeopathic medicine, their detection limits are about 100 times higher than the concentrations they say they put in. So they have absolutely no ability to detect if they have any of what they say they put in that. Only way homeopathic medicine works is if they're filler, the stuff they just happen to put in because they don't think it's going to do anything, actually works. So literally, it's random chance. Homeopathy just does not work at all. It's a kind of silly thing. And the way they think they're doing it is just a joke. Anyways, the slope of a calibration curve, this can tell you something about sensitivity. Some of the examples is this down here. Notice this method is more sensitive for perchlorate in reagent water than it is for groundwater. And so here we look in groundwater. We see that this is not particularly sensitive to groundwater. See that? We look here, reagent water, it's far more sensitive than reagent water, right? By the way, sensitivity is another thing that is not just more sensitive is better, period, congratulations. That's not like that. Like, you can be too sensitive. And so if you then have to dilute all your samples if you're too sensitive, okay? And that's why I was talking about machines that if you put in a sample that's too concentrated, you'll be outside your dynamic range. And even worse, you could damage your detector. Yeah. That's actually how speakers work too. Have you guys ever seen where somebody's like put an amp that's too powerful for the speakers and they blow the speakers? The speakers are overly sensitive. And the other way too. Have you ever like connect your phone or something to speakers, and it doesn't matter how high you put the speakers, you get like this crackling if you put it too high? That's because the signal coming off your phone is too small. Your speakers are not sensitive enough. So the acceptable blank values, blanks are going to account for interferences by other species in the sample, traces of analyte found in reagents used for sample preservation, preparation, and analysis. Notice oftentimes you will not be able to do a test immediately on large scales, especially in like factories and stuff. And so you will have to have some sort of preservation as well, okay? Frequent measurements of blanks detects whether analytes from previous samples is carried into subsequent analysis by adhering to vessels or instruments. Big problem. This is actually the reason that you typically want to go from low concentrations to high concentrations, by the way. Because if you go from high, some of the concentration can be left over. If you go from low, the concentration that's left over is proportionally much smaller. Okay? There's always a chance that some of your analyte that you're looking at will stick and stay on your instrument. Okay? And you don't get rid of it by whatever washing technique you're doing or whatever, right? It happens a lot. There's three methods, the method, reagent, and field blanks. These are the three different types of blanks that you can be talking about. Blanks is actually kind of this field unto itself. This is one of those places that people have a tendency to take to just think is going to work, and they don't think about it like they should. And so it's one of those places that tends to be sort of a blind spot, okay? Most of the times it works, and then that like 10% of the time, it just fails you horribly, and the person doing it doesn't understand blanks enough to be able to do anything about it. And so that's why they have to call somebody expensive in, somebody that knows what they're doing. So a method blank is going to be all the components except your analyte. This is taken through all steps of the analytical procedure. This is the primary blank we're going to be using in most of the experiments we do this semester, okay? And this is the blank that you've typically used, probably. I doubt you've used much of the other blanks. Subtract the response of the method blank for the response of the sample before calculating your quantity of analyte, and that's the typical blank we've talked about. You'll remember your like Viz spectroscopy. We did all the steps except for add the analyte, right? And so by the way, if you boil your analyte, you gotta boil this. If you do any process to your analyte, you should do it to this as well, okay? It just doesn't have the analyte. Everything else though. Reagent blank. This is similar to a method blank. It's very similar, but has not been subjected to all the sample preparation procedures. This is what bad labs typically do. And it works most of the time, but you're never going to know if it doesn't work. So you'll just get this time that your concentrations are all over the place and you don't understand what the hell is happening. You're getting peaks that you don't expect to get, probably because you're using a reagent blank. You're just taking the ingredients you have in your analyte and putting them in, rather than taking it through the whole process. Okay? A field blank. Oh, by the way, a reagent blank and a method blank, there are experiments where they're the exact same thing. Just in case you're curious. Okay? Like, we've done a few experiments in Gen Chem where technically it would be either, essentially. A field blank, this is going to indicate if the analyte is inadvertently picking up by exposure to field conditions. Essentially, this one is where you take it out into the field. And so you would everything, like if you're drawing blood, you would take this out in the field with you. You would do everything you're doing with the in the field with it, except for actually putting in like the blood sample. Okay? And these are actually fairly common on like biological tests, tests on people. You'll see a lot of those cards where you put like samples on them, or you'll see a lot of those like deals will have a little blank next to it, like a little sample that's next to it, or a little place in the card that you're not don't do anything. That's your field blank, actually. Matrix interferences. Sometimes responses to analytes can be decreased or increased by something else in your sample. So remember this word matrix. It is exactly what you might think it is, but a lot of people get confused. Okay? So a matrix is going to refer to everything in the sample other than the analyte. Remember the Matrix movies? It's like that. The analyte lives in the matrix, right? So everything around them's the matrix. I know. Kind of terrible example, but it works, doesn't it? So again, this example we showed before was actually matrix interferences, right? So we have a heavy matrix interference from groundwater. We have basically almost no interference from the reagent water. Probably no interference, but I would have to, run a test. All right, spike recovery. Spike, also called a fortification. This is a known quantity of analyte added to a sample to test whether the response to the spike is the same as that expected from a calibration curve. Spike samples are going to be analyzed in the same matters as the unknowns. So let's say you're testing drinking water, and it's found to contain 10 milligrams per liter of nitrate. You spike it 5 milligrams per liter. Ideally, what would happen when you spike it is the concentration would be 15 milligrams per liter, right? Because you added 5 to it. If you get a number anything other than 15 milligrams per liter, then you know you have matrix effects, right? Your matrix is interfering with your analyte. Do you understand how that works? Okay. This is a very powerful technique. And honestly, if you're starting up a testing technique, or you really should do this if you're starting a testing technique for sure. And if you are doing a testing technique or a testing regimen, you really should add a spike recovery step on a fairly regular basis. Okay? Because you can have things change. Like you could have cards being produced at factory, right? And suddenly the factory changes how they do the cards. Oh shit, now they have lead in them. Well, I'm testing for lead. I'm screwed now, aren't I? Not really. You just have to calibrate it out, right? And how can I do that? Well, I can put spike in, right? And see how things are changing. Okay? So a good, robust testing method can fix all of that. So this right here is the spike recovery formula. It's very simple, but it tends to be a little bit counterintuitive for many people. Okay? So your percent recovery is the concentration of the spiked sample minus the on-spiked sample. Okay? And that's divided by the concentration that you added to that sample. Now, one of the reasons that's not very intuitive is this is typically called the spike here, but you don't see spike, right? You see added, okay? I know, it's just, that is how it is. Whoever made this missed an opportunity to make this easier to figure out. But whatever, still, you know, it is what it is, and you can figure it out. Do you guys have any questions? Basically, it's the percent you recover of what you added, right? See that? That's all it is. It's actually just a basic percent recovery that you'd see in organic chemistry. That's it. So, calibration check. This is going to analyze solutions with known concentrations of analyte. A specification might, for example, call for 1 calibration check for every 10 samples. So every 10 samples you do a calibration check. And you'd see if your calibration is shifting over time, which happens a lot. So it is actually a very good thing to do. I'll be honest, this calibration check is usually, if you actually go through and check your specifications, there'll be specifications in every lab, and you're working in industry or a hospital or whatever, if you check those, I promise you that most labs are not going to be doing what it says they should be doing. And you're going to go, oh, yeah, we're not doing a good job. Yeah, it's not every 10, it's every 100. Because there's a lot of pressure to get samples turned around, right? And this obviously slows you down. But it's incredibly vital, actually. It keeps the lab from drifting off and giving bad results. Yeah. This is one of the most important things you can do to keep systematic errors out of your system. Quality control. Samples of known composition will be provided to the analyst as unknowns. This is actually very important that you don't label your quality control, which is what most labs do. Which is really fucking stupid. Because then your person's going to start doing what they're supposed to do instead of cutting all the corners that they did to go to lunch early, right? So if you make it unknown, they'll cut the corners like they normally do, and you can see the actual results you usually get. Okay? And it's very different. This helps eliminate bias introduced by an analyst who knows the concentration of the calibration checked sample and therefore might just, put the number. Or it may not be as bad as purposely cheating. It may just be as simple as if he gets a number that he doesn't think is right, he tests it again and gets the right number. That doesn't sound so bad, right? But you have to realize that on an unknown sample, he doesn't know what it's supposed to be, right? And so he would have given the first number, which was wrong. See the problem there? Okay, so remember, accuracy, this can be assessed by, well, first off, what's accuracy? How close are you to the true value? But you don't always know what the true value is. But anyways, how close are you statistically? How confident are you got the true value? Within your range, right? Precision, what's that? Yeah, how close your repetitions are, right? Specifically, this typically is more affected by things like systematic errors. This is more a measurement of random error, typically, okay? And so this typically is how close is your mean, and this one would be how large is your standard deviation, okay? Typically. This can be, the accuracy can be assessed by analyzing certified standards. Even better if you go ahead and introduce them as unknowns so the people don't know their standards. And somebody that's not involved in the testing can then evaluate. Calibration checks performed by the analyst, spikes made by the analyst, and analyzing blind quality control samples. By the way, every instrument should have a certified standard that they keep near the instrument, and you would just put it on and test it at a given time during the day. If you start drifting off, and then you can calibrate to that standard, okay? And you may have to remake them if they're liquid, but typically they try to make them solid, something durable. Even the balances have that, you know that, right? Even the balances come with standards. They're little like steel weights. Gauge precision. This would be replicate samples. This would be replicating portions of the same sample. You could break up a sample. If you're looking at concentration, you can break it up in any sections you want, right? And so you could put it on once, analyze it, put it on again, analyze it, do that a few times, and see how close you are together, right? And that tells you how repeatable your procedure is. Some procedures look really good, look like they'll be perfect, and then they're just not repeatable, okay? And that actually happens a lot in journals. Something like 30% of journal experimental procedures are not repeatable. When people try to repeat them, they can't. That used to be 40-something%, but there's been a big drive to reduce that and improve it. You know, it's just, did you put every step in? Most likely not. It's hard to do, right? Written standard operating procedures, SOP. This is absolutely vital to running large labs or running experiments in your publications that can be repeated, okay? This is where this fails a lot, is that poor SOPs. So these must be followed rigorously to avoid inadvertent changes in procedure that could affect the outcome. For example, if I say pipette, so you pipette 10 milliliters with a fixed volume pipette, okay? Okay. What if one person starts blowing it out every time? Instead of just whatever delivers? What if one person blows it out at the end? Yeah, they'll be systematically high, right? What if one person, when they deliver it, instead of holding it there for a bit, they just go? Because they're in a hurry. Too many samples. I'm probably going to have somebody systematically lower, right? And so that's going to affect it. It is implicit that everyone follows standard operating procedures. Adhering to those procedures will guard against the normal human desire to take shortcuts based on the assumptions that could be false. Like, it doesn't matter if I just go quickly, right? Everything that delivered, right? But that's not actually true, is it? Because a droplet can take longer to drop. And if you have a sideways motion while you're doing it, that's actually going to cause liquid not to come out, right? Because of centrifugal force. So it's difficult on first blush when you're working, in this moment in the procedure to know every aspect of what could go wrong. So be careful about cutting corners. Control charts. So the control chart is going to be a visual representation of the confidence intervals for measurements having a Gaussian distribution. This is going to warn us when a property being monitored strays dangerously far from an intended target value. This can be used to monitor accuracy, precision, or instrument performance as a function of time. And so here's a control chart. Notice they're essentially orders of standard deviation off. See that? So we'd have control values. This would be like a control sample that you give people as an unknown. And then they're reporting the results and you'd enter them, okay? And then, they vary around your mean, right? They're going to be off your mean. That's just facts. But you would have a set standard deviation off that you would accept, okay? If it breaches that set standard deviation, then you'd give a warning. You go, hey guys, make sure you follow that standard procedure. Then if you go beyond that action line, see the action line here, which is another standard deviation off, that's when you'd have to actually take action and, you may have to change the SOP so people can better follow it. That's actually a common thing, that your SOP is just difficult to understand. Or you have steps in there that just take too damn much time and you're giving people too many samples. So they literally can't do it. Okay? I mean, it happens both ways, where people are just screwing up, and then there's, your SOP is just not a good fit. You didn't consider something. Does anybody have any questions about this? This is actually an incredibly powerful tool right here, and actually very important when you're talking about legal. We're talking about labs. You got to remember, these labs, we're talking about labs that are going to determine if a person lives or dies many times, if they go to prison or not. This is really important stuff, right? Literally foundational to everything that we do. Also, we're talking about if Coca-Cola is the right mixture and gives you a consistent taste. Which is even more important, right? All right. Method validation. This is going to be the process of proving that an analytical method is acceptable for its intended purposes. We talked about the statistical part of that before. Now we're talking about actually doing it. Okay? So in validating a method, we'll typically demonstrate that the requirements are met for the specificity, linearity. Anybody know what the linearity is? Are we in the linear range? Okay? It's very important, because if we go beyond linear range, well, dynamic range will tell us the concentration, but not reliably, right? Kind of. At least we know it's changing. But if we go beyond that, we don't even know if it's changing, right? By the way, specificity and linearity are almost directly anti-correlated. They're almost opposites, okay? The more specificity and the more the limit of detection, the lower limit of detection, the easier it is to breach your dynamic range, typically, okay? Because remember, you're increasing that slope as you go up into the logarithmic function, right? That slope gets faster and faster. You see what I'm saying? So by increasing that slope, you have less concentration range that's within your dynamic region, right? Okay. So they're almost an opposite. Accuracy, precision, range, limit of technique of detection, limit of quantitation, and robustness. Robustness is a big one most scientists tend to forget. Like for me, I don't need a technique to be particularly robust because I have enough practice to perform pretty much flawlessly, over and over and over, right? But once I give that technique to people, other people, like my students, right? That's where I need that robustness to become much, much better. And typically, if I make all these other demands too high, my robustness becomes very bad. Okay? So you'll notice that many student labs, all of these are pretty low. That's because we've sacrificed them for robustness. In case you were curious. Specificity, again, this is the ability to distinguish the analyte from anything else. Linearity is usually measured by the square of the correlation coefficient for the calibration curve. Your types of precision are going to include your instrument precision, your intra-assay precision, your intermediate precision, and most generally, the interlaboratory precision. The Horwitz trumpet, this is an empirical statement that precision becomes poorer as the analyte concentration decreases. You can understand that statement, right? That's just basic science, isn't it? As your analyte concentration decreases, what happens? You have less and less to test, right? So any error becomes a larger and larger component. And you saw that in your glassware at the beginning of the semester. Notice that? The range is the concentration interval over which the linearity, accuracy, and precision are acceptable. This is related to the linearity dynamic range that we talked about. but that's not the only factors, okay? It's also the limit of detection. It's also, you know, as you get lower concentration, you can get less accurate, okay? So there's more to it than just the linearity range for that sample, the dynamic range. There's more factors. Detection limit or limit of detection, LOD, they're both the same thing. You can also just do DL for detection limit. It's just, you know, different words for it. Same thing. This is usually taken as 3 times the standard deviation of the blank. Why would it be 3 times the standard deviation of your blank, by the way? Because that gives you like a 99%-ish confidence interval that you have something, right? You see that? If you're lower than 3 times your blank, the standard deviation of your blank, then like if you were 1 standard deviation, you'd only be, there's a 30-something% chance that you didn't detect anything at all, right? You think you did, but you didn't. The lower limit of quantitation is 10 times the standard deviation of your blank. So detection limits are where you yes or no, do I have something? Okay? Did I get a change? Yes. Did I get a change? No. And so you're talking usually like a 99% confidence interval. You know, that's okay. I'm 99% confident that I got something, right? I don't know how much necessarily, but I got something. The lower limit of quantitation, it being 10 times standard deviation of your blank, this is where you could quantify how much you got, right? And so essentially we need 3 times 3. Anybody understand what I got that number from? Yeah, you have to have 3 points that are separated by your limit of detection, right? Which is times 3. So which gives you like 9, doesn't it? You go 1 more just to be sure, 10. You see why that's your typical limit of quantitation? Okay, the reporting limit is the concentration below which regulations will say that the analyte is reported as not detected, even when it is observed. So even though you think you've observed it, this reporting limit would be legally what has been shown to give good results on the sort of numbers that you talk about when you're talking about population, okay? So remember, yeah, you might be within the limit of quantitation, but that limit of quantitation may only be a 99% confidence interval, right? What would happen if I used that as a legal quantity? If that was my legal quantity for somebody being alive or dead? Just a really drastic example here. Well, let's say I test 100,000 people. How many times do I screw up at 99% confidence interval? 1,000 times. And I bury 1,000 people alive. Does that sound like a good idea? No. So, you know, my lower limit of quantitation, this is reasonable when you're talking about doing a few tests. But you need a reporting limit, something typically quite a bit higher than that, when you're talking about something that's going to be applied millions of times, right? It's just not good enough. Robustness, this is the ability of an analytical method to be unaffected by small changes in operating parameters. Something with good robustness will very reliably give you results, even if you were to put somebody in front of it that has a week of training. Okay? As long as they know how to operate it, kind of, it's going to give you a good result, and you'll be able to tell if it's wrong. Okay? And there are tests like that, by the way. There's some really good spectroscopy instruments that literally have like little barcode scanners, and then the person puts it in a feeder, and it feeds, and you get the result. And those things, robustness, you could probably hire a 5-year-old. And most of the time, you would be fine. Like if you had a manager over a 5-year-old, it'd be okay. You could hire a chimpanzee, train it really well, and you'd be all right. And those are what they usually use at the labs you see in the hospital around here. That's the sort of instrumentation they have. That's why a big company can come in and run those with relative ease, right? Okay. This is an example of detection limit. Do you guys have any questions about this? No? Did you guys look through this problem at all? Okay. Well, let me know if you have any questions. I don't think it's something that's particularly difficult, but, let me know. If you have any questions about it, we'll go back. Standard addition, this is going to be a known quantity of an analyte that's added to an unknown to increase the concentration of that analyte. The standard additions are especially useful when you have matrix effects because they can allow you to correct for those matrix effects and detect them. Essentially, it's a version of spiking, but it's a little bit more complex, okay? So it's very similar to what we did with spiking, but we're going to do a bit more work on it. So we use equation 5.7 to compute the quantity of analyte, x sub I, of course, after the single addition, standard addition. The initial concentration would be x sub I, which is the initial concentration initial, right? See, literally that's brackets, meaning concentration, right? X meaning unknown, sub I for initial, right? And so this is going to increase to x final, F, right? While the initial signal, that's Ix, intensity, meaning signal, right, of that initial unknown, the x. S of x is going to be your concentrations of the standard added. Notice that you could call this standard, or you could call that substrate, right? So it's the concentration of the S, because you know this, the standard. And again, this is the final because it's the final state, right? And again, that will give you a signal of x plus S for whatever method you're doing. Whether that was a spectroscopic method or whether that was a mass spectrometer, okay? Doesn't really matter. You can add just whatever signal. Okay, does that equation make sense? The signal is proportional to the amount added. Does that make sense? All right, so here we have a standard addition. We have an unknown concentration of the sodium. We have then the concentration final here. So a serum containing the sodium gave a signal of this in an atomic emission analysis. There's our signal right there, right? Notice these units always have to cancel. You see that okay? Make sure you're using the same units. Don't get tricked. Then we add 5 milliliters of the 0.08 molarity of sodium chloride, which would give us similar concentration, same concentration of the sodium, right? That we're adding. These were added to 95 milliliters of the serum. This spiked serum gave a signal of 7.98 MV. So we put that in. Find the original concentration of that. So right here, we can get, so we use 5.8, and that would give us a final concentration of sodium after your dilution. So you would enter this is the formula right here. It's just an MX, or same formula as you'd see like an MV equals MV2, right? Same sort of thing. The signal is proportional to the concentration. And so any increase in concentration gives you a similar increase in the sample, right? Or signal. And by the way, the assumption in this formula is that you're in the linear range. If you're not in linear range, then this would not work, right? Okay, so you plug these in, so you just increase the volume. Your concentrations had to increase. Your concentrations had to be diluted, excuse me. And then your standard addition right here. This gives you your concentrations for your samples. You plug these in, plug in this, solve for this term here. Don't forget to add these first before you multiply. This is a unitless number. It'll end up in molarity, whatever concentration you put in. And there you go. Does anybody have any questions about that? Don't forget the dilution step. So if you're given things like this, you're adding 5 mils to 95 mils, right? So that concentration is only 5% of your total concentration, right? You've diluted it considerably, 20 times, right? So if you put those large numbers in, you're going to get really messed up numbers, right? All right. So for multiple standard additions to a single solution, we would use equation 5.9 to construct the graph in figure 5.6, in which the x-intercept would give us the concentration of your analyte. Essentially, we're doing like a Beer's law, except we had an unknown concentration in the beginning. And so the x-intercept will actually give us the concentration. Does that make sense? We'll see in just a bit. For multiple solutions, we would make up the same final volume, and slightly different graph in 5.7 would be used. So keep in mind, this one right here, 5.9, and the graph 5.6 is for multiple additions to a single solution, okay? This one would be multiple solutions made to the same final volume, which is typically what you've done. The equation 5.10 will give the x-intercept uncertainty in either graph. This is the multiple solutions made up for your same final volume. So what we're going to get here is, notice that our original sample has analyte in it, right? And so our y-intercept is going to have a signal in it for that analyte in it, right? See that? The x-intercept would be the concentration. Please note there's not negative concentrations, right? So, get rid of the negative. But the x-intercept is the concentration of our original sample. These would be the standard additions that we make. Each of them would give a linear increase in our concentration, right? Each of them gives a linear increase in our signal. Okay. Does anybody have any questions about that? In practice, it's much easier than it sounds. You just graph it. So figure 5.7, 5 milliliters of unknown in each flask are diluted to 50 milliliters. If the x-intercept is 0.235 millimolar, what is the original concentration of analyte in the unknown? So your analyte was diluted by a factor of 5 to 50, right? And so that means that you have 10 in each flask, a 10 times difference, right? Okay. So your x-intercept in the final concentration of dilute sample was 2.35. That means your concentration in that sample was actually 10 times greater, right? Okay. And so you do the math, 10 times greater, right? 23.5. Okay, what time is it, by the way? Okay, we'll go ahead and call it a day. We'll finish this up next time. Just have a few slides left. This is going slow.